Well, welcome. Thank you for coming to the inaugural lecture in the MITRE College Lecture Series. As the name of the series implies, this is one of many fantastic lectures to come. This is part of a broader initiative to kind of broaden and deepen our connections with academia in the area. And we're very lucky today to have two excellent speakers from Worcester Polytechnic Institute, WPI for short. So I want to take about 2 minutes here. I'll try not to be too long. I've got some biographical information and some perhaps even anecdotes. No, just joking. We have Dr. Alex Wiglinski and his PhD student Travis Collins with us today. Travis is an electrical and computer engineering PhD student in the Wireless Innovation Laboratory of WPI. He has both his BS and MS degrees in ECE from WPI and is currently pursuing research in the areas of software-defined radio, cognitive radio, LTE and LTE advanced communications, wireless comm, and adaptive signal processing. Travis is generously supported by the MathWorks for his PhD research activities, so if you didn't catch a joke earlier, bring your gripes about MATLAB to Travis. Or praise, if there is any of that. Just joking. All right, so Alex M. Wiglinski is an associate professor of electrical and computer engineering at Worcester Polytechnic Institute and is also the director of the Wireless Innovation Laboratory. His research interests are in wireless communications, specializing in cognitive and software-defined radio, cyber-physical systems, cognitive radio and electromagnetic spectrum security, and wireless system optimization and adaptation. Alex has been or is currently sponsored by DARPA, the NRL, the Office of Naval Research, the AFRL, the Space Vehicles Directorate within there, the MathWorks, Toyota, Raytheon, MIT Lincoln Labs, NASA, just to name a few, and NSF, of course. Alex also recently worked a sabbatical here, finished up in December, so he took a sabbatical with J82E, so he's a bit familiar with MITRE. He's also a senior member of the IEEE, as well as a member of Sigma Chi and Eta Kappa Nu. And one final remark about Alex, anybody who's had him as a teacher, he is very widely regarded and held in high regards by students, current and former, as a dynamic, energetic, and engaging individual. So without further ado, let's welcome Alex and Travis for their talk. Thank you.
Okay, good. So this is working. So thank you, Joe, for that wonderful introduction, and thank you all for spending this beautiful Friday here indoors with Travis and myself on this inaugural lecture series. Hopefully, we'll continue with other exciting lectures from WPI and surrounding institutions. So as Joe mentioned, my name is Alex Wiglinski. So I did my sabbatical leave. I think the section numbers change. I was like in 536, so it's J82E now, and it was a great experience. It got me to sort of broaden my horizons. At the same time, a lot of my activities, seeing where they're deeply rooted in cognitive radio and software-defined radio, and at the same time, folks like Travis and my other graduate students in my team at WPI were very interested in sort of pushing the boundaries of this technology. And so today's lecture sort of touches upon some of the areas that we've looked at or are going to look at, as well as those that are kind of quite active and we're currently pursuing. Okay, so in particular, and in fact, I have a workshop that I'm trying to get up and running. We're currently soliciting papers at the IEEE conference on communications and network security. It's going to be in San Francisco later this year, and we actually have a workshop called CRESS, Cognitive Radio and Electromagnetic Spectrum Security. And this is sort of an area of emerging interest, and we'll be talking a little bit about some of the sort of salient features behind security of cognitive radio engines and where they are applied. Okay, so in terms of presentation, we'll first of all talk about cognitive radio. So sounds really cool. You go to a psychologist, they'll think something totally different than what a communications person is thinking about. But there is a method behind the madness behind naming this type of communication technology cognitive radio. And in particular, it leads to the second point, which is machine learning. Okay? So we'll talk a little bit about the different types of machine learning techniques that are out there, and then do a case study. This was actually some of the work of one of my PhD students who recently graduated, Dee Poo, in terms of something called primary user emulation attacks, or PUE attacks. Then we'll switch gears, and Travis will discuss a little bit about how cognitive radio security, in particular, the decision-making engine that is sort of at the core of any cognitive radio system, its vulnerabilities and ways of assessing it. In particular, one real-world application of cognitive radio. So can you buy cognitive radio? Well, not exactly. You can't go onto Amazon.com and type in cognitive radio and it's like, or eBay and say, buy one now for like $2,000 or something. No, in reality, cognitive radio is this concept, and a lot of the features people are thinking about being deployed in next generation wireless systems. So if you look at 5G, you go on Wikipedia and they say, oh yeah, cognitive radio features like interference mitigation and coexistence, and everything's automatic and there's an aspect of learning that's involved, right? But we don't imagine that these systems will be operational and standardized until 2020 at the earliest. Maybe, right? So what Travis is going to do is focus on one specific example that is relevant to today's world, which is self-organizing networks. They have a lot of cognitive radio-like features, and the SON engine is very similar to what the cognitive radio engine achieves. So we're going to use that as sort of our case study. And in reality, a SON engine still does not achieve true learning in the sort of basic definition of what a cognitive radio engine does, but it has a lot of the same sort of features and characteristics. So it's a great way to look at a real-world example and relate it to cognitive radio, because this is something that, given sort of the current abilities of radios and where they're heading, I think it's worth exploring sort of the current technology. So if we can build security in at the beginning, we don't have any gotchas later on. We'll then summarize what we've talked about and sort of like walk-away points for this presentation. Okay? So cognitive radio overview. So the question is, like, I mentioned this before, what is a cognitive radio? The definition. So some of the slides I sort of resurrected from the last time I gave a talk here in 2012, May 2012 here at MITRE, but it's good to sort of get back to basics. So what is a cognitive radio? And what a cognitive radio is, so this is one definition from Wikipedia. Oh, dear. So what happens is a type of two-way radio that automatically changes its transmission or reception parameters in such a way that the entire wireless communication network of which it is a node communicates efficiently while avoiding interference with licensed or unlicensed users. And so folks at Virginia Tech, they actually define it as a software-defined radio with a cognitive engine brain. Okay, so this is verbatim from Wikipedia, right? Like, that's a reputable, citable source. No, just kidding. But what happens is this sort of gives the gist of what a cognitive radio is, which is essentially it's a wireless platform. It then, based on the environmental stimuli, so that could be external, like the wireless channel, the network load that it's connected to, as well as, let's say, battery supply, right? Or any other sort of parameters that affects wireless transmission performance. It says, okay, I have this sort of current environment. This is what the user is expecting in terms of optimal performance. And then all these parameters, operational parameters, let's say even modulation schemes, the number of antennas that are being used, the data rates, everything is tweaked in order to achieve the best possible performance for a human user. Now, there are a lot of things that are left out, right? Because, for instance, like a lot of people say, oh, SNR. This SNR will achieve this possible performance with the human user. Well, is there a correlation between that and, let's say, what a human perceives as acceptable performance, right? Like a video. Is there an actual one-to-one mapping between, let's say, the SNR of the transmission channel and someone watching a video? I can tolerate maybe some delays or some MPEG errors. Maybe someone else is not. So there's a psychology aspect. There's also policy aspects, economic aspects. So there, for instance, I might get the best possible performance, but whoa, I don't want to pay that much money. And so, for me, that's not such a great performance. So there are a lot of other interdisciplinary aspects of cognitive radio. But from just a very basic engineering perspective, wireless communication engineering perspective, A cognitive radio is all about the radio reacts to the environment and tries to give the best possible performance to the human end user, the human user. And all of this is related by mathematics, right? There are equations that relate environment to, let's say, some sort of metric, and then that metric's fed into, let's say, another metric that says, this is how you rate the entire environment to, let's say, the outcome, which is the end user performance. Whether it's data rate, latency, or just successful transmission across a challenging environment. So in a nutshell, that's what cognitive radio is. But when you say it to a lot of people, they come up with different definitions, right? So cognitive radio, people think it's intelligent, it's agile, it enables, let's say, minimal interference, some sort of interference avoidance scheme, maximum bandwidth, spectrally agile. A lot of people associate cognitive radio with dynamic spectrum access. Oh, this spectrum is no longer accessible, I'm going to go here. Sort of, but more and more people think of cognitive radio as a platform that maybe it does not dynamically access spectrum, but on the fly will try and adapt its operation parameters to the environment around it. And if it encounters something that it's never seen before, will base its outcome on past experiences and learn, coming up with a new set of configurations. It might get burned. It might say, ooh, this is totally awful. So there needs to be almost like a feedback loop from the human operator and user themselves to say, oh, no, this is not good. And it's like, oh, okay, I'll try another configuration, right? So there's a lot of different feedback loops in this type of system. So cognitive radio right now, if you go to a conference and you see cognitive radio, some papers, I have to admit, will just sprinkle cognitive radio and say, and MIMO, right? And it's mostly MIMO, not so much cognitive radio. So the true cognitive radio type of works will involve some sort of adaptability. And even that is not cognitive radio. I remember for my job interview, one of my hosts asked me, oh, so Wi-Fi is cognitive radio. And didn't want to offend the host. I said, oh, yeah, it's kind of cognitive radio. Like, no, that's adaptation, right? It's built in. It's like, oh, I have this SNR, switch to this mode. Where's the learning? Where's sort of that on-the-fly decision-making in the case of, let's say, a new environment that never encounters before, right? Okay. So there's a history. And this is from one of the books I wrote from 2009. So what happens is there's a history behind getting to cognitive radio, which is up here, okay? And let's say starting off with a regular hardware radio. So first of all, the hardware radio, that's sort of like the tried and true type of communication system. Maybe it was all analog for the most part, and you have things like CB radio and shared channel maritime communications, and that's around the days of Marconi, all the way into about the 1960s, and then computer technology kicked in, right? So then we hit the next level, which is software-controlled radio. So in that case, what happens is perhaps you still have analog components, but for the most part, you have essentially tunable radio. So the software will say, oh, okay, we're encountering this environment. Let's say we have an equalizer that's software controlled, but you still have, let's say, a lot of the the baseband functionalities in an analog domain. And this ties into, among other things, a lot of communication engineers see it, but even in my own students, I find that those students that understand software-defined radio, which is the next generation, there is a heavy computer engineering component to it. The two worlds are doing this. If you do comms and you understand modulation and equalization and filtering, that's great. But the implementation side of the house is more and more becoming digital. It's more and more becoming computer architecture related, computer engineering related. And it's shown here when people said, oh, gee whiz, I can actually incorporate computer technology. So remember the transistors, like the 1940s, and then you began having somewhat capable computing platforms that can be employed with radio systems. Well, that's great. And then software-defined radio, someone says, if I have a fast enough A to D, D to A converter, I can digitize everything and use digital filters and digital modulation schemes instead of the analog stuff. right? And the faster the A to D and D to A, the more throughput you can handle, the more filtering, the more complex operations you can have. Of course, what happened is, in those days, the computer technology in the 1990s, like speakeasy, I always love this example. It's like, it fit in the back of a truck, right? So nowadays, like Raspberry Pis and ARM Cortex A9s and stuff, your cell phone, right? How much computational horsepower is in that? Lots, right? And so this gave rise to things like the DSA radios, the dynamic spectrum access radios, where, again, you have to have high computational horsepower to make decisions saying, oh, spectrum occupied, go to another spectrum. Oh, it's occupied here, and jump all over the place, right? Because a human user, like let's suppose I give one of these units to my mom. Wonderful lady, but she'll like say, well, what am I supposed to do now? You know, no, let the radio take care of that. And then finally, cognitive radio. We have all this horsepower. We have, and it's miniaturized. Maybe we're not at a stage where we can fit on a cell phone yet, although I've seen software-defined radio platforms that are getting there really, really quickly, right? But what happens is we need to come up with algorithms. We need to come up with the architecture, and some have been proposed, in order to achieve this sort of like learning aspect on top of these sort of software toolboxes, if you will, of implementing different modulation schemes and performing various actions, and also awareness. So there's a sensing aspect both on the platform and the environment around us. And then there are a lot of other issues, such as spectrum regulation, which I think is beginning to catch up. So I actually have a Google alert. So every morning at like 6:30, that's my wake-up call. It's like a bunch of Google alerts pop up. And one of them is wireless spectrum. And it's cool, like, oh, AT&T and Verizon and others are like trying to vie for new spectrum. And then I think Microsoft Research is trying to do dynamic spectrum access in Africa. And then you have Google with their balloons trying to beam down Wi-Fi. So there's a lot of things going on because everyone sees sort of the business opportunities. Everyone also knows about the scarcity of wireless spectrum, which I'll talk about in a few minutes. Oh, yes. And this is part of the reason, is this demand. This is kind of an old chart. This is from 2008. So I haven't updated this in quite a while, but you can, assuming that the trend continued, look at the, just looking at this trend, we have 262 million subscribers in June of 2008. And I think at that time, the population in the US was about 300 million. I'm not sure where it is now. It's probably 30 million more. But what happens is that's a heck of a lot of subscribers just for one technology. Now there's Wi-Fi, and there's all these other wireless appliances all over the place using very specific limited bands, right? And this is just these types of guys. And let's not even talk about LTE and LTA. Which spectrum are they going to access in order to support the society's insatiable demand for more and more connectivity, right? And so you might wonder, okay, well, that's great. 262 million subscribers. How much did they talk? Well, if you're a parent and you have teenagers and you have a plan, right? You probably, it's like, how much did you spend talking this week? Well, although I would have to say voice minutes have been going down. Texting, on the other hand, is a different story altogether, right? But, and this trend, you can probably see it in this chart. But in 2008, 1.1 trillion minutes were spoken. And you can see that it's kind of declining because now if you ask my students in my class, they don't talk on their cell phones in my class. No, it's like, it's all texting but horrifically, lots of data services, especially streaming video. The number of people that's like, hey, I'm going to watch this, like let's say Family Guy on my iPhone and stuff, right? Imagine how bandwidth intensive that is, right? It's probably even worse than voice. Voice is simple, right? You just filter to 4 kilohertz and digitize that. I don't know what sort of bandwidth you have and needs in terms of like streaming video. Okay, and this actually leads to the spectrum scarcity issue. And so if you look at any sort of spectrum chart from the US, from England, from Canada, all of them look the same or more or less. And there is a design for this. And what happens is the ITU sort of tries to standardize as much as possible many countries sort of their spectrum regulations and allocations, because it would be really poor, like, it would be difficult if you design a TV in one country and, oh, you export it. Well, you have to change the RF design because it uses a totally different frequency band, right? But for the most part, you notice lots of allocations between 0 and 6 gigahertz and beyond, right? Like, and that's even 0 to 3 gigahertz is kind of like where we really want to be in terms of wireless transmission. Any higher, and then you don't have the nice favorable transmission properties for like nice long-range communication systems, right? So what happens is we're sort of like maxing out spectrum allocations in the traditional sense. Okay, we need a bidder, okay? I'll bid $2 billion on this chunk of spectrum to do X, Y, Z, and then you can check up with me in 5 years and see that I built it out and service these clients and such. Well, what happens is that model, unfortunately, is not all that efficient. It might have been great when we had, a limited number of wireless users using static wireless devices, but what happens is, and this is from my book, what happens is, for the most part, you have chunks of spectrum, and I think, do I have GPS in here? Probably, but what happens is you have chunks of spectrum that are used, but temporally, like you don't have, except for TV, well, there are some applications like TV that are always on. So you know that they are using their spectrum, their 6 megahertz channel constantly. However, we don't use all TV channels. How many people here watch TV over the air? Yeah, good. How many of you installed your own TV antennas on your own roofs? Yeah, oh, cool. Okay, so I'm not the only one that's raising the hand, okay, because my wife thinks I'm crazy. But once they started scrambling the basic cable channels, like we have cable by internet, and then I installed, we took another cable and connected to our TV, and then it's like, hey, wait, there's no Big Bang Theory. What's going on? And then she's like, I want TV now. So I said, okay, fine. Okay. Anyways, okay. What happens is other applications might temporally be on and off, and in addition to that, might not use up the entire frequency as well. So what happens is it's inefficiently being used, right? So it's almost like the license holders have exclusive rights over the spectrum, and what happens is they may or may not use it 100% of the time. So why not build up a scheme where we can borrow spectrum and be able to access it when, let's say, the primary license holder is not using it. So the idea is called dynamic spectrum access, okay? And what happens is we use spectrum when it's not being used by the primary license holder. So we preserve the legal exclusive access that these license holders have sort of, like, they obtained through these auctioning processes. They built up their infrastructure around it. And when they're not using spectrum, we can borrow it. Now, there's some things, there's some problems with this model. Like, are you sure this radio is not going to interfere with my license transmission? Oh, 99.99% sure. Not 99.999% sure, So there's that. So there's trust in the technology. And then the other thing is the business model. Imagine if those secondary users are offering a competing service, and they didn't have to invest as much as the license holder. Oh, so this is where the socio-economic, political policy side of things, and I think there's a conference called TPRS, which only talks about this. So it's a bunch of lawyers and economists and political scientists that get together and talk about the non-technical side of technology. Oh, it's so cool, okay? So you've probably seen this in every digital comms textbook, right? You have your baseband functionality, and this can be programmable. And then you have the RF side, which I won't talk too much about, that is tunable, right? So with the software-defined radio and also like MEMS technology, like microelectronic, blah. I forgot what. Mechanical systems, thank you. So microelectronic mechanical systems, you can make these RF segments tunable. Some people, there's 1 or 2 companies out there, I believe, that just literally spit out digital signals. They're A to D converter. It's like, oh, you modulate in the digital domain up to this gigahertz carrier frequency and then over the channel. I forgot, there's a company in Albany, but I need to double check that. Someone just mentioned to me in passing. So this is all great. This flexibility, agility, automation, but we need intelligence behind it. So what I'm going to lead into, okay, we're not going to talk about too much about dynamic spectrum access right away, but we want to talk more about what are the different opportunities in terms of making that intelligence. And we turn to the CS side of the house. I'm not a CS major. I have an ECE background. But I've done enough with artificial intelligence and machine learning techniques to sort of like at least put in perspective, like, the thing is, the folks in CS, they've done this, they optimized this work to a T. But in terms of applying it to a communication problem, this is where the ECE side of the house comes into play, okay? And so what happens is we need to look at our cognitive radio as a black box. So we have this box. We have, just like what I mentioned before, the environmental parameters, the dials. We have the knobs. So based on what we sense in the environment, could be channel quality, the signal quality, the network load, desktop applications. So yeah, what application are you running off of that radio? Are you watching YouTube? Are you sending email? Are you doing internet messaging? So each one of them will have a specific load and a specific expectation. Let's say the human user, like, are they watching the video intently? My wife, for instance, is kind of interesting. She likes running Netflix or something in the background, but then she's like doing her work, right? So she doesn't really care about the video quality, it's really audio quality. Can we use that to our advantage? Do we need to use that much bandwidth, right? So again, there's a psychology aspect to that, right? So, and then there's also the target experiences. So that would tie into what the human's expecting. Then there's also the allowable configurations. Maybe our radio cannot support MIMO. Maybe our radio cannot support that modulation scheme. Maybe our radio cannot do this type of equalization. And then we download that and tweak it using these dials, knobs, in order to get the best possible performance. What I did not show here is that feedback loop, right? So, and I think Travis has several feedback loops he would like to show you guys in a few minutes, okay? So this is, in the long run, so the target network experience, this is what you want, this is what you see, this is what you can do, okay, in terms of what's in the software library that you can put into the baseband operation of your radios. And then finally, this is what you can tune, like, the fine tuning, right? And so another way of looking at this, and this is from the IEEE SEC 41 standard, and I think they changed their name again to IEEE DISPAN, which is now confusing because there's also a conference called IEEE DISPAN. But we won't get into that. This actually shows a lot of the feedback loops that are incorporated. You have the hardware platform, TX and RX. You have a decision database. So this is like all past decisions that the cognitive radio has. Your learning and reasoning, oh, typo. This interfaces with the database. It's like, have we ever experienced a similar situation? Yes or no? Yes? Use the decision from that. That gives you the optimal performance. No? Okay, what can we do? What would be the configuration based on past experiences? Let's try this out. And it's based on sensing your environment. What's available out there? And it could be a variety of things, like the radio environment and stuff, as well as tied into the policies and rules of the country, right? Some are more strict than others. And so this also came from my book in 2009. Okay, so where do we get that intelligence? Well, that's the second part. So there are a variety of different approaches. And so the cognitive engine decision making is really dependent on what you put in as parameters. So radio parameters, environmental parameters, performance objectives, right? And what happens is it all is tied to how you mathematically relate. So, it's great. You can intuitively say, oh, if I have this SNR, I'm going to have this type of performance under these conditions. But again, let's go back to the computer engineering side of the house. What does that mean? In the end, we have to relate this to computing technology, right? So this is where we need to relate all of these relationships in something that the computer that's running the cognitive radio understands, or the microprocessor embedded system, which is mathematical equations, right? So we need to relate that, and now we enter the realm of multi-objective optimization. Okay? And at the same time, there are a few approaches that we can use in order to get the best possible performance. So we have these mathematical relationships. We have these multi-objective fitness functions, if you will. And then we need some sort of architecture to help us reach that somehow very quickly. And there's a variety of ways. So you probably heard of genetic algorithms. Another great name, right? So in terms of buzzwords and stuff. But genetic algorithms are often used in order to achieve that. I like to call it an intelligent guessing game with biologically inspired parameters, right? They choose definitions like mutation and crossover, like almost brings me back to my biology class days, right? But it is kind of handy if you set it up right. There's also rule-based systems, like expert systems, where it's like, if you go and get a car part, oh, I have a Subaru 2014 Outback basic edition, blah, 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 blah. Oh, you need this oil filter. How's that done? Because, the computer database is an expert system. They'll say, or you can choose one of 3 oil filters. This is the cheapest. This is high performance. And this one's so-so, and it's being phased out. Oh, I'll go with the cheapest, please. So what happens is you have rule-based systems, not really so much learning, but it does sort of fit the bill, kind of like what Wi-Fi does in terms of trying to match the parameters in the environment to configurations and tunability on the radio side. And case-based reasoning is similar to that. Okay, so first of all, parameters. So we have things like transmit power, modulation type, bandwidth, coding rate, frame size, time division, duplexing, symbol rate. So there are a variety of different radio parameters that we can control and use in our optimization. We also have environmental measurements, right? So path loss. Can we hear the signal? How well can we hear it? If we know what the transmitted power level is, what are we expecting and how do we reverse it? How do we amplify it at the receiver? Noise power, how much noise is in the environment? The battery life, most people don't think about this, but suppose you have a wireless system, and suppose you don't have a power supply that's the size of a car battery. What do? Battery life is quite a serious issue, especially if you put into the field and such. Power consumption as well, and then spectrum. So the big thing you'll see in a cognitive radio symposium or cognitive radio conference, everyone's talking about spectrum and interference avoidance and interference mitigation. Even in LTE and LTA papers and publications, everybody's talking about interference avoidance. You have 2 femtocells, they're in adjacent apartment buildings. How do they not interfere with each other? How do they mitigate any sort of interference with each other? And so that's the environment. And there's a variety of other parameters that we talk about when we deal with environments as well. And then finally, the radio performance objectives. There are a variety. So bit error rate, we want to minimize that. Maximum throughput, power consumption, interference, spectrum efficiency. These are some, but perhaps some higher level is like, how about the human, right? So like seriously, like, think about like, how does like bit rate correlate to, let's say, that streaming video? Well, you also have like some sort of source coding and video coding. And so all I care about is how many MPEG errors do I have, right? The big green blotch or the pausing, if you will, of that streaming video, or latency. Let's say I'm in a Skype session. And then all of a sudden it's like, hello, is anyone there? And then 2 seconds later, ooh, very irritating. How do you relate that as a performance metric, right? Okay. So the funny thing is, these performance metrics, these radio parameters, and the environmental aspects of environmental measurements of these radios, they're all intertwined, and sometimes they're conflicting. So what ends up happening is you have relationships between, let's say, minimizing BER and the radio parameters. You have, like, let's say, maximize throughput with some others, minimizing power. So what ends up happening is we have these relationships that sort of intertwine and could potentially be conflicting with each other. So now, how do you optimize for multiple, let's say, goals or objectives when you have a finite set of parameters and sometimes they're conflicting with each other? Now what you've got to do is sort of set priorities between what you hope to achieve and what you can tune. In fact, that's just PhD material right there. Like what some folks use, and let me see if I have a slide on it. Ah, yes. So there's something called multi-objective. Well, there's one thing called multi-objective genetic algorithms, or MOGA. And what happens is the principle behind it is you have like these individual fitness functions, these single objectives, like minimize bit error rate, minimize spectrum inefficiency, and all that. And then you put a weighing factor, sum it all together, and then it gives you a score. Ta-da! And then that's what a computer understands. However, how do you choose the weights, right? And this is always like, whenever I see PhD students bring this up and they try and defend their theses or they're giving it a presentation, and it's like the first question everybody asks is, how do you select those weights? Are they optimal? That's just PhD gold right there. And again, some folks in the CS domain, actually all they do is figuring out the optimality of this weight. So this is, again, more of a machine learning concept than anything else. And then there's a variety of different constraints. Like you want all those weights to sum up to 1. So you make sure that your score is between 0 and 1, right? And then down here, we mentioned about the five objectives as a sample, right? And they're weighed like between W1 and W5. And so choosing those weights, like let's say for me, spectral efficiency by far is the most important. I would give it 0.8 out of 1. And then everything else I would weigh accordingly. But again, how do you choose that? And so that's an open area of research. Maybe another chapter in your thesis, right? Yeah, there we go. So what ends up happening is there are a variety of different solutions. You can use the exact method, which we'll talk about, expert systems. There is heuristic methods, like neural networks and genetic algorithms. And then you have something like case-based reasoning with genetic algorithms. Okay? So exact methods, some great things are you get the solution. It's like just like when you go to CAP, auto supply or whatever, and say, here's the model of my car. I need an oil filter. Give me something. And it gives you. It doesn't try to optimize and say, oh, I think this oil filter is going to fit your car and give you this type of performance. No, no, no. It's like go into the database, and it fishes out, these are the appropriate oil filters. Please choose one based on what you think is the right price point and performance, right? Don't go to, yeah. The only problem is you need to have, first of all, like the disadvantages usually requires some sort of complex equations, and there's a time complexity associated with this. So what happens is in order to derive that list, well, you better have, it will take a long time to derive just the right equation in order to come up with these rules, and that in itself. So the lead time to creating that optimal solution is quite large. Maybe it's not even achievable, right? So that's why with the expert system, it's you have an expert, and case-based reasoning is also similar to that. You have an expert comes up with these rules, and maybe there's some assumptions made. So it's only as good as your assumptions. You can also do like let's say some sort of like true optimization algorithm. Here's like my equation describing, let's say, some sort of fitness functions or set of fitness functions. You send it through something like Newton-Raphson or something. It tries to find the optimal point, but it might take forever. It might not even be achievable in real time. So you might have to do this offline in advance. Then heuristic, lower complexity than exact, less research usage. And then what happens is you have a little bit more flexibility, but doesn't give you the optimal solution necessarily. So for instance, like the exact solution would be the expert system, right? So you have the expert. So I did this at University of Kansas when I was there before going to WPI. And I worked with a bunch of computer scientists, and they were all great about the AI and the expert systems and such, and I was the expert. So they turned to me and they say, okay, what's this signal to noise ratio thing? I need to understand it. What's this bandwidth thing? What's this bit error rate thing? And then they would pick my brain, and then they would make a little equation, right? And then ta-da, we produced a book chapter and a journal paper, and the computer science community was like, wow, expert system in wireless communications, that's really awesome. But for instance, the expert system here, quick and dirty, it's like usually quite limited. And so you need a domain expert. So AKA me, if you go to a computer scientist, you would be that expert. So they will pick your mind in terms of like, how do you come up with that function and such? And what happens is, you would have some sort of like language that you would communicate. So if the frequency of interest is in use, alter frequency by X amount, right? That would be sort of like, what the expert would say. It's like, yeah, we're too close to that frequency. Let's move over by this many hertz. And then like the working storage, you would have like, let's say a variety of parameters. And there's one really cool software out there. It's been around for, I don't know even how long, but CLIPS. So that's what Travis is looking into right now. I think it was initially produced by NASA, and I believe it's open source, right? So it's open source, you can download it. You too can have fun with expert systems and play with it. And it has a specific language to it, and you just write it out just as much as you would have here, sort of like in a sentence, and create that expert system. The next one is the famous genetic algorithms. So basically what happens is you have a space with all possible configurations. You select randomly from that space X number of chromosomes. So, just like in genetics, it's like, so I have all these possible combinations of chromosomes that define the radio, right? The DNA of the radio. I subselect N out of that large group. And then I test each one of those out. And I see which one yields the best possible performance, or close enough, right? Then what happens is I take those that did well, and I mutate them, right? Crossover, tweak a few parameters, try it again, and then discard the ones that were not so great, and repeat and repeat and repeat, and hopefully we converge to a performance that's doing not that bad. But the problem is there is that convergence time. How many iterations do you need to do in order to achieve this? Okay? And then lastly, case-based reasoning is literally, here's my parameters. Like, you measure it across, like, let's say you have 10, 15 parameters of the measurements, if you will, of the radio, the environment and such, and goes into this array, and it says, oh, you got this SNR, this bandwidth, this, let's say, this amount of spectrum efficiency, blah, blah, blah. This is what you want. This is the case you want to choose. Configure a radio like this, right? So that's case-based reasoning. There's a problem with case-based reasoning. It's brittle. What happens if it's not 25 dB in terms of SNR? It's 25.1 and there's no case. Falls through, right? And so what you might need to do is there's something called fuzzy logic. So it's like, 25.1 is close to 25. OK, give you this case, right? So there are a variety of different AI techniques, and there are others. So I had one PhD student, which work we'll talk about now, that used neural networks. And neural networks are tricky because black boxes that you've got to train and then employ, right? So that's the primary user emulation attack. You might wonder, what's primary user emulation attack? Suppose you're a licensed user, and then you allow your spectrum to be used by these unlicensed guys as long as they promise that they won't interfere with you. So no one ever really talks about how the unlicensed guys play with each other. Their only mantra, do not interfere with the primary user, right? So if I see a TV signal, I stay clear away from him. But then I'm duking it out with all the other primary users, secondary users, right? What happens if I make myself look like a primary user, right? In terms of the spectral signature, the traffic behavior and such. Oh, I've just upped my priority. Oh, don't touch him. It's like, right? So what happens is the secondary users mimic the spectral characteristics of the primary user. So how do you detect that? So what you can do, so this is an example. So you have a bunch of primary users. I'm a PU. I'm a primary user. I'm a licensed user in the spectrum. And then you have secondary users that are transmitting. And then here's this guy, and he's like saying, I really want access to. I'm going to cloak myself as a primary user as well. I'm going to change my spectral characteristics. And then what happens is the other secondary users, oh, I have to obey, right? Otherwise, I'm in violation of that important rule. So the conventional techniques, people have looked at location-based techniques, energy detectors, but energy detectors have too high a misdetection rate. Match filter detection, you require additional hardware and software. Why not use a computer, right? Why don't you use the embedded technology and signal processing at your fingertips? And then finally, location-based only works if you have static users for the most part, right? Oh, what's that TV transmitter doing sitting here instead of like, in Waltham and stuff? So, but if it's a mobile user, all bets are off, right? So what we looked at, so there are two approaches that we looked at during these dissertation research. We did a combination of energy detection to see who's out there, cyclostationary to extract the signatures of the signals of those users, and then an artificial neural network to say, aha, you are a legit primary user. You're an imposter, right? The other technique, this was pretty cool. There was a friend of mine from BU, and he's an image processing guy, and he came along and he says, okay, like, he was talking about his image processing thing, and I never knew image processing could be so much fun. So what happens is he was doing something called action image recognition. So he had this video of someone playing tennis, and he had this algorithm to detect whether it's a slam or whatever sort of return, different motions, and based on those images said, aha, this action's happening. What happens if you apply that to the spectral signature of a wireless communication signal? And that's what we looked at in the second approach. So this was the first approach. And this was actually published in GlobeCom 2011. And so it broke down into, is anyone there? Characterize the intercepted signal once you found them. Figure out who it is based on their cyclostationary features, then determine, is the analysis good enough? So we put a threshold. If it's kind of dodgy, then we try again. And then what happens is we make the decision. Imposter or legit user. Or it could also be a legit secondary user. That's fine. And so there are a variety of different types of cyclostationary detection schemes. We use the spectral coherence function. And there's not enough time to talk about this wonderful. There's lots and lots of math and probability. So I think for Friday, I'll spare you guys that. But what happens is you get really cool plots, each one of which is like your unique fingerprint to what signal is being transmitted. Roll-off factor for your raised cosine filters, modulation scheme is a multi-carrier. All of that is given away by these SOFs, okay? And then the other technique, the one thing to pay attention to is we don't use cyclostationary feature detection because it's still computationally expensive. Just use action image recognition techniques instead. So what we have is there's a variety of different types of action descriptor calculations that we can perform. And so what ends up happening is we use that and look at the actions in spectrum of what's happening, and we use like one of these, we calculate the vector, we create a covariance descriptor of the feature vectors, and then we take the log covariance of these descriptors. And what ends up happening is we then use the neural network, okay? And what we found is that the performance is slightly better when we use the action recognition technique over the cyclostationary method. And this is all computer simulation results, right? But to get to the point, we actually implement this on a USRP2. So that was actually pretty cool, that we were able to employ this in hardware, but there was a lot of non-real-time processing, of course, on the computer itself and such. So I think these slides will be made available afterwards, right? So lots of literature out on this, most of them written by Dee. So she's working nearby in analog devices. So she's only in, was it Woburn, right? Woburn? Or Wilmington, sorry, Wilmington. OK, so now I'm going to turn the floor over to Travis. And he'll talk a little bit more about cognitive radio engines. Oh, lots of time, lots of time.
10 minutes?
No,
All right.
no.
Let's see if we can zip through this. So I'm going to be talking about cognitive radio engine security, primarily focused on LTE and SON and LTE-A, if you're familiar with those. I'm going to discuss traditional attacks on LTE, things that like the military, like your techniques don't really work in this sense because of how the network is structured. But let's begin with so the cognitive cycle itself. So Professor discussed like his black box where you had like the information coming in and your knowledge center and then your knobs at the end that you're turning. So if we simplify this a little bit, you have like your sensing portion. You have your sensors that come in with your data, like in a network that'll be like your towers or something, or your UEs, your user equipment. And then you'll feed that into your learning section, and you'll make a decision and analyze the data that you're looking at and adapt based on some objective that you have. Okay, but this is actually kind of vulnerable in many situations because how do you know that you can trust the data that's coming into your system? Is that data being spoofed by some user? Is it being corrupted? Is like that sensor being nulled in some way? How can you trust that data? And at the learning side, how can we kind of go around this corrupted data or your spoof data? Can we utilize historical information? Can we use other towers that are around you to kind of like vote out anomalies in your network? Can we use other attributes that an attacker might not have access to make a better decision? Or can we just inject some noise into our system? So if you are in like some mode that you shouldn't be in, the system will kind of like nudge itself out eventually. Okay. So some software strategies that are common to like an adapting system would be to first like define your threat model. What does the attacker have access to? What can he affect in my system? What can he change in my sensors? Okay, and then based on this, you explore what the failure modes that can happen in your system. Where do I not want to be at certain times? And then you'll develop some way of detecting this and some mitigation. Maybe like you'll push out a patch eventually, and then eventually it'll become part of your design of your system. And then you'll develop new models, new threat models, and see if you're still resilient to similar problems. Okay. And this brings us to LTE. Okay. And in LTE, or LTEA specifically, we get introduced to something called SON. SON stands for Self-Organizing Network. I don't know if you're familiar with SON, but a lot of the attributes actually existed in previous releases of LTE, primarily the planning and the deploy methods within SON. So SON has three areas that are defined by the standard. And the first is the actual planning stage, where you do some massive network simulations. They can take days or weeks, and you'll figure out, all right, I need another tower in this location. Like a new stadium is being built here, so I'm going to need more towers around these locations. And that will determine where your towers will be. The second step is actually deploy. So you actually send out a technician, put up a tower, and you hit a button, and it downloads the configuration data automatically and looks at towers around it. It's called automatic neighbor recognition or relation, ANR. There's a ton of acronyms in LTE. And this is supposed to be automatic in SON. Traditionally, you'd have like a technician out there and be out there for hours trying to figure out, all right, I know I got towers around me in some location. And then once everything's set up, you move into the optimize phase, which is where you optimize things like handover or load balancing. And you'll heal the network if, say, a tower goes down. And things have come out like ICIC, which is intercell interference coordination, I think. And there'll be optimizations on load balancing and handover and energy savings. And these are big parts of what LTEA and SON are doing. So the SON engine itself, the main goal really is to limit human interaction. So you don't have like an operator playing with a lot of knobs in your network. The network will react in real time, or you hope in real time. So, and that's going to actually depend on the architecture of your network. So there's three main architecture designs. The first is a kind of like a centralized architecture where all of your sensors feed into one master node. Think of it kind of like Brainiac is making like all the decisions across your whole network in a region. The second is a distributed. This is actually a fast acting, so the decisions are made on the towers themselves rather than in a central location. So these decisions will be fast, unlike the centralized, which will be on the order of minutes. The distributed will be on like in real time. Okay, but the decisions won't be optimal, as we would say. But in reality, you're going to have like a hybrid approach where you're going to have decisions being made in both locations. For example, like in a hybrid approach, you'll have your towers doing handoff optimization, but you might have like a top node knowing that ahead of time that, say, the Patriots are in town, we need to allocate more resources around Foxborough. So and that's what we're going to see eventually when SON is fully deployed. Okay. So the engine behind SON, the goal is to be predictive, goal-oriented. The main goal in SON is performance. They don't really care that much about security. And the research problems that I've really run into with my work is that there's kind of like two versions of SON. So you have SON that's like at the very low level, like optimization handover. And that's what academia is concerned with. And then there's like the turnkey solution, the overlay of your whole network. You introduce SON, and boom, you get a 200% increase in performance. And again, they're all about performance, and they don't really care about what can actually go wrong with your network. So security in LTE, traditionally, it's been focused around privacy and authentication. So you don't want people accessing your network, and you don't want people reading data they shouldn't be on your network. So this is kind of like the guy climbing up the telephone pole in the 80s to see like he can pick up any phone call that he wants in your network. So since GSM focused on these networks, when this got pushed into LTE or evolved into LTE, they really only focused on this privacy and authentication model, where they kind of just pushed it over to crypto and said, okay, yeah, let's increase our cryptographic algorithms, and that will solve the problem for us. So a big problem is like these networks aren't really robust to jamming of any sort, unlike military networks. So you're not going to do like your frequency hopping or your spread spectrum stuff. And this is so you can get more performance out of your network. So the traditional attacks, I've kind of split them up into two areas, your DOS and your DDoS. DOS is like more like focused on a single tower, and your DDoS is on like your network level, your group of towers or your region. And then we'll discuss future attacks on SON itself. Okay, so this is actually a picture of a tower in, I think, Jersey that caught fire during maintenance. I wouldn't want to be the owner of that one. So you can do high-power jamming against a tower, which doesn't really work if you're like mobile, because you run out of power really fast. Control channel jamming. Jeff Reed, who's kind of like a forefather in software-defined radio, is really looking at control channel jamming in LTE. So let's just go look for it. So this is a LTE grid structure, if you're familiar with it. And the blue and purpley gray areas are your control signals. So you knock those out, which is a really small sliver of your whole signal, and nobody has LTE service within range of you. So there's also like software bugs, since towers are now like software-defined radios or software-controlled radios or software-controlled networks. They're susceptible to like the same bugs and viruses that your desktop machines can get. And also there's this interesting idea of weaponized femtocells. A group in Germany, well actually, if you're not familiar with a femtocell, it's kind of like this router-looking thing that you attach to your home internet connection, and it's a small or mini cell tower for you. But a group in Germany actually took one of these home, reverse engineered it, and they broke the kind of privacy and authentication boundary in the cellular network. So they could like snoop all the traffic, and they could look at, they could basically authenticate anybody that they wanted to into their network. And then there's the DDoS, distributed denial of service attacks that exist. Cellular botnets, which is kind of a interesting topic in computer science that a lot of people are looking at, since everyone's got a smartphone nowadays, and eventually every device will have some sort of internet connectivity. Like your fridge will have LTE access eventually. And with 5G and the Internet of Things, it just becomes more and more of a problem. And IPv6 kind of compounds this problem, so everyone is IP addressable. You don't, like, NAT is not a firewall. And these attacks, so you'll get a bunch of vulnerable machines, install some malware on them, and kind of like launch an attack on some centralized location in your network, like a home subscriber service, your HSS. You attack that, and no one can make a call within. Usually, they're set up by zip codes. So if they attack that HSS, then no one in, say, like New York can make a cell phone call. Okay, so now let's move to SON. So since SON is more like in very kind of like a niche growing field now, you have to look at it in kind of chunks or pieces. And this is looking at a handover optimization that is being developed. This was developed by a bunch of researchers at Nokia, I believe. So first of all, handover, how it works in LTE is going to work. Yeah. Okay. So your UE takes some measurements. A UE is like user equipment, it's like a cell phone or something, and it will return some data to the tower you're connected to. And then the tower will say, all right, am I within a certain threshold of my ISNR or my received signal strength or something like that? And when you reach some threshold, it will say, OK, let's hand you over. Let's hand you over to some target tower that I think you're near. And then you'll do some discussion with the target tower, and then you'll tell the UE to reattach to the new tower. Okay. So in SON, what's going to happen is that when you make this decision on this guy to switch over to the tower, and then you switch over, if an event happens, like you hand over too late or too early, or event called a ping pong, where you go to the next tower and then you bounce back, the original one, the LTE system, the SON algorithm will actually adapt and say, all right, who was at fault in this situation? So when that happens, it will actually change the thresholds of when it does handover. And it will actually sometimes change what tower you get routed to. So if you kind of play with this, the inputs a little bit here, say if you send fake measurements to the source tower that you're connected to, or you refuse to do the handover, or you force in a late handover, you can actually adapt what the algorithm is doing and tell, or you can actually start routing traffic, if you do this enough, around certain cells, or force cells to become very small based on these handover thresholds. So how do we go about testing this kind of thing? Software simulation is only going to go so far. Since these cognitive algorithms are aware, or environmentally aware, you're going to be extremely limited by your simulation or how you perceive the world in your simulation. So we really wanted to do hardware simulations or hardware tests with this, and develop our own kind of cognitive engine. Right now we're looking at CLIPS as our own cognitive engine, but it forces us to build this awareness into our system. And then eventually develop defensive methods or like hardening techniques that you can use when you develop a SON algorithm. So this is actually a cluster that I built in our laboratory. It's a bunch of Linux machines that have software-defined radios connected to them. And the system is pretty automatic. You define a node, and it will deploy software to a PC, and they'll be defined as like a tower or a user. And we control everything from the physical layer all the way up to, we're actually working on the Mac right now, doing some work with that. Originally, this was set up with CSMA, so we're pushing over to OFDMA. The testbed itself uses USRP 210s. I don't know if you're familiar with them. We use them a lot. They're used a lot in academia. They're interesting little radios. And again, our cluster is fully automatic. You just have a configuration script that we built, and it does the test for you. We rely primarily on MATLAB. So in an academic environment, it takes a long time to kind of train new people on new software. And I used GNU Radio a lot in the past, and that's just been a nightmare to bring new engineers onto, especially PhD students. It's been a little interesting. And MATLAB's great, and I'm also being funded by them, so that kind of sways my decisions a little bit. But we use CodeGen, which allows us to operate in real time. And HDL is coming soon, so you can actually deploy like a full OFDM receiver to the FPGA on the USRP. And we do some multi-threading in MATLAB, which is kind of like our own version of MATLAB. So some work we're doing is we're completing the OFDMA Mac layer. I'm working with a summer student in undergrad to kind of put the finishing touches on this. And then we're going to finish up change the uplink to SCFDMA, which is what LTE uses. Right now, you can just use the backbone of the network itself. Or you can use SMA. The current protocol that we use is kind of like a contention-based scheme for on the uplink. And then once the OFDM layer is complete, we're going to apply our network level optimization and test robustness. And Professor mentioned the clip system. I'm digging into that now. It is very old school, so we'll see how that works out.
Okay. Okay. Well, thanks. I guess I'll just wrap things up. Thank you. Quickly with just one slide. So a lot of text though. Again, like I think the main point, and I think this is something that's kind of interesting from a communications perspective, is sort of the increasing involvement of microprocessor systems, embedded systems, and how they're being employed in communication systems. Like you know, just like 5 years ago, we had USRP 1s and 2s, and they were attached by gigabit Ethernet or USB 2 connections off of a computer workstation, and your capabilities were primarily limited by how powerful your computing station is. And nowadays, for instance, I believe Analog Devices has like a FM comms 1 and comms 2. You connect it to a Z board that has a Zinc 7000 FPGA with 2 ARM Cortexes on it. And it's quite a nice platform and such. And things are just getting smaller and smaller. I think there's even a product that's being sold in India right now for $350 that supports 0 to 6 gigahertz, and it can be interfaced with LabVIEW, MATLAB, Simulink, and your own custom C, C++ code. So really, we're pushing the envelope in terms of, you know, as computing technology is becoming very versatile, as well as the RF front ends, this now creates new opportunities for intelligent communication systems with a wide variety of functionality. And that cognitive radio-based wireless communication systems are becoming a reality. I remember several years ago, people say, you know, Alex, like, you know, between you and me, off the record, do you think cognitive radio will actually become a reality? I think everybody's asking me that because, you know, do you have that, can you actually get that onboard intelligence and that real-time decision making? And, you know, 5 years ago, you know, given the technology at that time, I would say, I think it's a nice buzzword, but I think we'll get close to it. Nowadays, seeing what we're seeing now, I think it's more and more becoming likely. We're seeing it in SON engines. There's no learning in SON engines, but it's becoming quite close to that. And then with 5G, and given what the features people want to have in that, even more so, I think cognitive radio will become more and more a reality, and we'll see it embedded in a lot of these wireless applications. But the trickiness, like what Travis mentioned, is the fact that how do you evaluate cognitive radio systems, right? So you have this thing that's almost organic or has its own life, and how do you test it? Theoretical derivations, it's a little tricky, right? Computer simulations are only as good as the simulator and all the models it has. And so we really do end up resorting to either using sort of emulated test environments or hardware test beds, like, you know, like what Travis developed at WPI is a starting point, of course. And well, one of the beautiful features, as opposed to a lot of solutions out there, it supports multi-user sort of interfacing. So you have a single base station, and you have or 2 base stations and multiple users accessing that. And that's what we're working on right now. Even a lot of like the solutions out there, like test equipment vendors and such, it's usually single UE with access point. And that, you know, you can only test so much in that environment. But what happens if you have 2 UEs, 2 access points, or eNode Bs and such? So really, I think, you know, as the complexity environment takes off, we're going to get into a very sort of interesting territory, and it will be very difficult to describe, like, you know, especially security, it's sort of the unknown of unknowns. We don't know what we don't know, and we go into that in a very complex environment, it becomes rather tricky. And we only looked at the physical and MAC layer. I have another student, Nick DeMoranis, who's actually working on the protocol network layer of such. So cellular botnet attacks, weaponized femtocells, that's his sort of like research area that he's exploring for his thesis research. So this is very exciting times. It's great to see that you know, we'll both be employed for a little bit longer. And it produces some very interesting research. It would also be great to interface with those economists and lawyers and political scientists and psychologists, trying to relate the ultimate performance with what we're trying to do. So for more information, so I can be reached at actually my email address. You can get rid of the ECE, but that should still work. Or at www.wireless@wpi.edu. Travis's email is traviscollins, one word, at wpi.edu. Not sure. You also have a GitHub too, right? Yeah. So you can download code from there. So if anyone has any questions, feel free to. If let's say if you don't have time today, you can always reach us offline afterwards. And again, thank you for your time. It's been great talking with all of you, sort of sharing what we're doing, and we'll be happy to take any questions. Thank you. Karaoke.
Okay, we have some questions. So if you're in this room, we'll start with you. Can you just make sure you try to use a mic for the recording? Thank you.
This might be a question for Travis. From the point of view of an adversary, what is the advantage to me if I am attacking a SON network of moving the traffic around to one node or the other? Why would I want to do that?
That's a good question. Let me think. So if you had a specific tower in your network that you know a lot of traffic will go through eventually, or is it like a metropolitan hub, then you could affect that engine so it will force an offloading of traffic onto farther away towers that will have worse performance for those users in that range. So that's one way I could see you pushing or shaping traffic in your network for in a bad way.
I'm just changing.
We're kind of still exploring the consequences of what happens when you actually do these things in your network.
Well, you tie up resources, right? So if let's say you do a handoff, right? So what happens is, I think in LTE-A you have the X2 channel, if I'm not mistaken. So what happens is the two E node Bs are just like bouncing back and forth, saying, oh, now he's in your court. Oh, now he's in your court. And so what happens is, by keeping the network tied up, you deny resources to other users within the vicinity of that E node B. So how much resources, how much bandwidth, how much time? I think that's sort of a quantitative assessment, and that's one of the things that we would need to find out. Maybe in the simulation world. So if you have like NS3 and you can build it up to be accurate enough to an LTE environment, I think there is an LTE model that's in there. Like there's a group from CTTC in University Politecnica Catalunya. So they have a model there. But in hardware, it would be really nice to see like how much resources that sort of attack would take. It's just keep your E node B constantly working and chewing on trying to accommodate that additional mobile user.
Yeah. So the basic answer is it will degrade the performance of your network to some degree by shifting the towers to a non-optimal load.
Could you actually affect the denial of service if you're routing all traffic through one tower?
So you mean if all of your botnet was concentrated on one tower, and then you wanted to, so there's a bunch of papers on whether like a tower would withstand that kind of throughput. It's going to depend on where they're located and how much traffic they're pushing, but it is possible to do that. And I've read a bunch of papers that have done it with like I think 2 towers, and they've brought down like part of the like a core element of a network. But it's going to depend on the distribution. And generally, so a botnet will be distributed among a bunch of towers, so it's going to be hard to defend against. Like DDoSs are very difficult to defend against in reality. Computer scientists don't have a good solution yet. Their real solution is, patch your systems and scan for viruses. That's the best thing we've come up with yet, because the other solutions are very expensive.
All right, thank you. Any other questions here locally? Yep, any questions down in Washington? Oh, one more question here.
Okay, this is about the primary user attack emulation attack. Seems like the, well, I guess you had the energy detection as your first step, and you're a grad student, I guess.
Yep.
It should be. Seems like that would be the upper bound on your probability of detection of the primary user. So was there any, or does the cyclostationarity aspect give you an effective SNR gain to, because you're not going to have probability 1 of classifying it correctly, so it seems like you could have a degraded performance even though you did this more sophisticated technique.
Yeah, that's an excellent question. I think, so the only difference between the two approaches, the action recognition versus the cyclostationary, was that first step, identifying who's there. And so right off the bat, spread spectrum communications would not work, right? Because the energy detector is like, all clear, and it's underneath the radar and all that. However, I think that was just like a first stab at this. So knowing who's there in the first place is kind of important. So in a spread spectrum network, this would not work. However, if let's say it's a TV network, that would be a different story altogether. Like, you would have that beautiful rectangular-looking spectrum with a little pilot tone on one side. Hey, there's another one, and we can classify that. So this would be for very much for non-spectrum, spread spectrum type of networks. Now, cyclostationary detection would work in, let's say, noisy environment with let's say very weak signals and such. And then in that case, knowing who's out there, and then the same information would be leveraged against it in terms of classifying whether it's legit or an imposter. So that's true. So the energy detection would be the bottleneck in both algorithms cases. If you're dealing with something with UWB or direct sequence spread spectrum signatures, yeah, that's true.
And
that's good.
Each of the techniques also has limitations on the differences that they can determine between the different users. So cyclostationary will do modulation schemes, but of certain classes. So QAM and higher orders of QAM, you can't really distinguish them.
Yeah.
But QAM and
and PSK or there are other aspects. The nice thing about the both techniques, the action recognition and the cyclostationary also, is we didn't look at the temporal behavior. So because let's say you have someone that looks like a TV signal, but why are they so intermittent, right? Then that would also be a dead giveaway. So it's really looking for multiple smoking guns to try and minimize sort of a PUE attack from working essentially. So that would be yeah. But I think the bottleneck would be that action, the first part.
Well, I guess with the classifier itself, was it trained more to identify emulators, or still to identify the true ones? Because that's slightly different, right?
So what happens is the assumption is everybody has a signature, right? And then what would happen is one of these secondary users would try and mask their PSD to look like something else, right? And then what happens is based on the type of data, so the action recognition is over time and across frequency. So basically your image would be the spectrogram. So you would look at that and you would see, oh, this doesn't seem to jive traditionally with, let's say, a TV signal would look like. And so that's where the neural network kicks in. It's it will say, okay, you train it on an actual TV signal, and you would say, okay, classify this as a TV signal, and if you don't get that, then it's something else. And so over frequency and time, it's going to look at the characteristics and say, no, this guy is definitely not a TV signal, or whichever. In this case, we didn't use an actual TV signal. We just used two guys of I think they were in the same modulation family, but with different roll-off factors and different types of traffic. And so they were you can call it out as opposed to, let's say it's a smash as a, whatever sort of tennis move. So yeah, good question.
All right, thank you. I think we have time for maybe one more question, either locally or, yes.
So the first level would be identify the location. That seems to be the easiest for the PUE.
Oh yeah. So if it's not, so if like assuming that this is like
Can you repeat the question?
well, oh, so maybe just to repeat the question. So the question is the first part, like the easy part for the PUE is to know who's there and who's not there. Is that correct?
Well, it has specific location for the primary versus the,
Exactly. So if you have like a licensed spectrum,
so you define the distance precisely, that would be the first line of defense.
yeah. So you're saying like if we have a licensed spectrum, we have a specific user, primary user that uses that spectrum.
Exactly located.
Well, that's the thing. Like, we're trying to move away from the location-based techniques because let's say we have a collection of legitimate primary users that are mobile. Let's say they're on I-90 or it's a university campus. If it's a TV tower, then it's quite clear. Like, the TV towers, you can probably see it for like 5-6 miles in any which direction, and it has a very known location as opposed to, let's say, you won't find TV towers in some person's apartment building. But suppose it's a different type of environment where there is some nomadic or mobile characteristic to these wireless users and belongs to either a centralized or maybe even it's distributed. We didn't really look at the different types of architectures. What we wanted to do is if we're in an environment where we have users and they're transmitting, we could sort of sort out who's who in terms of are they primary? Secondary, they would have a different characteristic, and then there's secondary users who try to mask their identity, at least from a physical perspective, in terms of PSD, to look like a primary user, to trick the secondary users. Now the thing is, we would probably need to use some sort of primary user emulation attack detector on the secondary users ultimately. So they would need this information because the primary user doesn't care about the fraudulent primary user, the imposter, because there's a set number of guidelines, and if they're interfered with, they talk with the FCC, and then the FCC goes after those guys. The secondary users, nobody really knows. No one's really specifying how secondary users access licensed spectrum with each other. There's a lot of talk about game theory, cooperative communications, databases. There's like some fears, like in the TV spectrum, that, okay, 802.22 has been ratified as a standard, and now people think all secondary users are equal, but some are more equal than others, right? And so they would have a higher priority secondary user access over other secondary user access. Like also 802.11 AF is another one with, so people are concerned about how among secondary users, who has priority over who, right? And so this is a way, not so much attacking the primary user, but beating out all the other secondary user applications, right? So it's almost like you want priority access in traffic. This might be illegal, but paint your car like a state trooper car, wear a uniform, put lights on top, and just send it off, and everyone's going to move away, right? So, and that's what we're trying to avoid in this circumstance. Welcome.
Let's thank the speakers one more time. Thank you.
Thank you. Thank you.